In today's video, we're going to be looking at 11.2b and the other half of part C as well. So this is looking at hypothesis testing when we don't know that population standard deviation. We only have a sample standard deviation that we can use to estimate the population standard deviation. Because of that, we can't use that z value, that z-score, that we used as our test statistic before, because remember, if we don't know our population standard deviation, we cannot find that z-score because it's within the formula for the z transformation. So instead, what we're going to do is use that sample standard deviation as an estimate for that population standard deviation in that formula. But if you remember back to when we did confidence intervals, that actually gave us something called a student's t-distribution. So we actually end up with a t-value rather than a z-value, okay? But the actual formulation of this is almost exactly the same as what we've done before. It's just that now our test statistic is going to look very slightly different. I'll quickly write down what that test statistic is, and then we can talk about it. I'll take that out for a second. We'll write it as that. Okay. So this is the value that is going to be used as our test statistic. Now, remember, a t-value that we get is only dependent on two things. Number one is an area, just like when you do inverse norm in a calculator to find a z-value, it will ask for an area. That is the probability that is to the left of that z-value, okay? Exactly the same when we do t-values, okay? For a t-value, the area is always the area to the left of the value under that curve, okay? So it asks for the area, and it also asks for the degrees of freedom. So a t-value or a t-score depends on, number one, the area under the curve to the left of the value, and secondly, it's the degrees of freedom. And the degrees of freedom is just the sample size minus 1. Okay, if you remember that from when we did our confidence intervals. So that's the two things that this thing will depend on. Okay, we use this much more than when we do the z-test for hypothesis testing. We actually use a t-test much more. The reason is because if you think about the way that we formulated that, when we did a z-test, you had to know that population standard deviation, because instead of an s that we have in this formula, when we found z, it asked for the population standard deviation sigma. The reason that we conduct a hypothesis test normally in this case is because we want to know whether the population mean is what we think it is. We are testing what the population mean is, whether it's the value that we think it is, or from some sample data that we've accumulated, is it actually bigger, smaller, or just different than what we initially thought. Okay, so we are testing that population mean because we're not entirely sure what it is. Well, if we're not entirely sure what our population mean is, we're hardly going to know what our population standard deviation is. So in most real world examples, this is the test that we actually use. A t-test is used far more than a z-test because you normally don't know the population standard deviation. You only know the standard deviation of the sample. So we just use that S value for the sample standard deviation instead of using the population standard deviation. Let's do an example. This is actually in the notes. If you go to the Google Drive, you will actually see the two examples that I'm going through in 11.2b notes. So if you want to follow along on the Google Drive notes, I would do that. The first example says that a researcher has designed a questionnaire she believes will take an average of 35 minutes to complete. Suppose the random samples of 20 employees finds that the mean time to take the test is 29 minutes with a standard deviation of 8 minutes. Determine if there is sufficient evidence to conclude that the mean time of the new test differs from the old one. Assume the population is normally distributed and conduct the test at the 0.05 level. Okay, so it's set up in very much the same way. The only difference is that we now have a sample standard deviation as opposed to a population standard deviation. We're going to go through the same steps that we did last time. It's just that our test statistic is now slightly different. So step 1 was to find our null and alternative hypotheses. We actually want to see what we're testing. Okay, so in this hypothesis test, okay, they think that the population mean is 35 minutes, but they have taken a sample and they have seen that the mean time of the sample is 29 minutes. But all they are saying here is that if you look, they just want to see if the mean time of the new test differs from the old one. They don't want to see if it's less than or greater than, even though in the sample the test was actually quicker than the population mean, so the mean time that they thought it would take to take this test. But even though that mean is smaller, they're just looking at whether the mean is different from what they initially thought. So the null hypothesis, as we said, it's always that the mean is equal to what they thought it was. You always have equality when you do the null hypothesis. For the alternative hypothesis, they're testing just whether the mean is different from what they thought it was, because they've got some sample data that suggests otherwise. Okay, so we've got our null and alternative hypotheses. The next step, that was step 1. Step 2 is just to find the significance level. And that is always given in the problem. So find the significance level alpha. And in this case, they want to conduct the test at the 0.05 level. So alpha is 0.05. Okay, that means that we want to reject our null hypothesis 5% of the time. Okay, the other 95%, we want to accept that null hypothesis for what it is. Okay. Step 3 is to find the test statistic. Okay, so we want to find the test statistic. Now in this case, as I said, we have been given a sample standard deviation, not a population standard deviation. If they gave you a population standard deviation, you're going to use a z-value. If they give you a sample standard deviation, you use this t-value. So we know that we have a sample standard deviation. So this is the formula that we will use for our test statistic. All this is doing is taking a t-score, a t-value, for the sample mean that we have been given. Very much the same. It's the same formula that we used when we did these confidence intervals and we had to find a t-value. It's very much the same, okay? So we know that our sample mean is 29. The population mean was 35. It's the value that we initially thought it was. The sample standard deviation was 8 and the sample size was 20. If you work that out, your value is negative 3.35. Okay, so that is our test statistic value. The next step is that we need to find a critical value, because then we can compare our critical value to our test statistic, and that is what's going to determine whether we reject or fail to reject that null hypothesis. So step 4 is to find the critical value. Okay. Critical value is always found depending on what your significance level is, okay? It always depends on that significance level alpha. When you do this, okay, a student's t distribution looks very, very much like a normal distribution. And the greater your sample size is, the more it's going to look like a normal distribution, okay? So let's say it's actually slightly flatter than a normal distribution, but it looks very much the same, okay? We want, in this case, we have a two-sided alternative hypothesis, okay? which means it's two-tailed. We know that our significance level is 0.05. Because we have a two-tailed test at the 0.05 significance level, we know that we need to have 0.025 on either tail. So at the lower end, we want 0.025, and at the upper end, we want 0.025. If you had a one-tailed test, whether it be left or right-tailed, you would put that whole 0.05 in either the left or the right tail. But we know that we have a two-tailed test here, as we have a two-sided alternative hypothesis with a does not equal. So because of that, we're going to end up with two different critical values. Okay, we're going to have one here and one here, and the area under the curve to the left of this t value, we'll call it t1, is 0.025, and the area to the right of this t value, we'll call it t2, is also 0.025. Okay, so if our test statistic falls either to the right of this t value or to the left of this t value, it's going to fall in that intolerance zone. It's going to fall within that 5% of the time that we want to reject our null hypothesis. Okay, so if we've got 5% between the two of those areas, we know that we're going to have 95% in the middle. Okay, and if our t value, if our test statistic was to fall in this range, we know that we would fail to reject our null hypothesis. Okay, and we're going to accept it for what it is, and we're going to say that the mean is still 35. Okay, so we've got to find t1 and t2. Now, the way that you do this is to use inverse t on your calculator. So when you found a z value, you used inverse norm. To find a t value, you use inverse t. Okay, it's found in exactly the same place on your calculator. So if you go to second and vars and scroll down, it's option 4. And you will see it will ask you for two things. The first thing is the area. The second thing is the degrees of freedom. The area, as always, is the area to the left of the t value that you want. So it's the area under the curve to the left of the t value. So to find t1, it's going to be inverse t of 0.025. And the degrees of freedom, okay, it's always the sample size minus 1, which in this case would be 20 minus 1, which is 19. Okay. If you do that, you should find that the t value is negative 2.093. Okay. And in the same way, if you do this for t2, okay, t2, the area to the left of it is going to be 0.025 plus 0.95, which is 0.975. And again, it's got the same degrees of freedom, which would give you the positive of that value, 2.093. Okay. Now we want to see where our test statistic lies. Okay. So if we look at our test statistic, it was negative 3.35. So let's look at where that is on our diagram. So T1 was negative 2.093. T2 was 2.093. We had for our test statistic negative 3.35, which means that our t value, our test statistic, lies somewhere over here, okay? It's going to be to the left of negative 2.093, okay? So our t value falls here, which means it's in that intolerance zone, which means that we must have to reject that null hypothesis. So step 5 is to determine, step 5, determine whether to reject H0 or not. Okay, so in this case, because t is equal to negative 3.35, falls in that intolerance zone, okay? So the area where we know that we want to reject our null hypothesis, that 5% of the time, we reject the null hypothesis. Okay? So we know that we want to reject our null hypothesis in favour of the alternative. So that tells us always go back for step 6, always put it back in terms of the original problem. So in this case, your conclusion would be that the new test actually does not take 35 minutes. Now, we don't know from our test whether it takes less than or greater than 35 minutes because we've only tested that it's different than 35 minutes. Okay, so even though our sample suggested it was less than, we can't determine that right now from the hypothesis test that we have conducted. Okay, so all we can say in terms of the problem is because we reject our null hypothesis, it means that the new test does not take 35 minutes. It actually just takes a different time than 35 minutes. Okay, so always relate it back to the original problem. Okay. So the next question that we have, I'm going to do another problem here that is a one-tailed test. And it says that an engineer designed a valve that will regulate water pressure on a car engine. The engineer designed the valve such that it would produce a mean pressure of 5.5 pounds per square inch. It is believed the value performs above specifications. Okay, so far what we have in this problem is we have been given that we think the mean is 5.5 and they want to conduct a hypothesis test to see whether this valve performs above specifications. The valve was tested on 18 engines and the mean pressure was 5.6 pounds per square inch with standard deviation of 0.08. Assume the population is normally distributed and a level of significance of 0.01 is used. Okay, so we want to test this. So we know that, given the information, our null hypothesis is that the mean is 5.5, that it hasn't changed. Now we want to test whether this valve, given, this should be HA, our alternative hypothesis, we want to test whether the valve actually performs above specifications because we have some sample data that suggests it. Okay, so we want to see if in fact our mean is greater than 5.5. Okay, so we have our null and alternative hypothesis and we want to test this. Okay. Now, I'm going to do this the shorter way. Again, you can do it the way that we just did, okay? In this case, you are dealing with a one-tailed test, okay? Your significance level is 0.01, okay? And you are dealing with a one-tailed test. So what you would be doing here is, again, finding your test statistic using a t-value where you take the sample mean minus the population mean of 5.5 divided by that sample standard deviation of 0.8 over the square root of the sample size, which was 18. Okay, so you could go ahead and find that test statistic. You can then find the critical value. In this case, it is a one-tailed test, and it is actually right-tailed. Okay, because you have a greater than, it means it's right-tailed, so your tail is going to be over here. So again, if you draw a sketch of this, okay, this time it is one-tailed. Your tail is going to be at the right because you've got a greater than. And your significance level of 0.01 will all be in that one tail. So it means that your area under here is 0.01. Your area here is 0.99 for a total of 1. And then this would be your critical value. We'll call it T1. So again, you can figure out T1. Okay, T1 in this case would be inverse T. Okay. Your area to the left of it is 0.99. Your degrees of freedom, again, is the sample size minus 1, which would be 17. Okay, so you can go ahead, find that critical value. You can find your test statistic, and you can see whether your test statistic falls in this danger zone over here, that intolerance zone, where we would reject our null hypothesis. Okay, that would be the long way of doing it. But as always, there is a shorter way of doing it, which is on your calculator using t-test. So when we did this before, when we did a z-test, we knew what our population standard deviation was. This time we only know our sample standard deviation. So in a very similar way, like I said before, when we deal with confidence intervals, when you know your sample standard deviation instead of your population standard deviation, we know we're dealing with t-values like we said before. So now we are going to be conducting a t-test because we know our sample standard deviation but not our population standard deviation. So let's go to stat and go across to tests. And right underneath where we had z-test is t-test. You're going to go to t-test and it's going to ask you a bunch of information which you can pull from the problem. So if you go onto the Google Drive and actually look at the problem that we have, it's right at the bottom of the second page, and we already know that the population mean that we had was 5.5. We're hypothesizing as to whether the mean is actually greater than 5.5. Okay, now we've been given statistics in this problem. If you look at it, we know what our sample mean is. We know what the sample standard deviation on a calculator, it's denoted SX. We know what that sample standard deviation is. We know how many things were in the sample, and we know whether we're looking at a does not equal, a less than, or a greater than problem. If you were given data, you would just put your list of data into your calculator and then you would hit data instead of statistics. But in this problem, we have statistics. So we know that our population standard deviation, the thing that we're hypothesizing whether it's true or not, that goes in the top under mu0. So that was 5.5. Then in our problem, the sample had a mean of 5.6. The standard deviation of that sample was 0.8. There were 18 engines in this sample. We already said that our alternative hypothesis was a greater than. And then we're going to go ahead and calculate. And it's going to give you all of this information. Okay. Now, as I said before, there's a long way of doing it, which we've already looked at, but there's a short way of doing it. And that is to compare this p-value to the alpha value in the problem. If p is greater than alpha, then you're going to fail to reject. If p is less than alpha, then we actually reject the null hypothesis. Now, in this case, if you look at the problem, we have stated that alpha is 0.01. Well, p being 0.301 is way greater than 0.01. So we know that in this case, we fail to reject the null hypothesis. It's always the case that if p is greater than alpha, you fail to reject. If p is less than alpha, you reject that null hypothesis. It's the same with z-tests and t-tests. Okay, so we already know from this p-value that we're going to fail to reject the null hypothesis. Okay, we're taking h0 as true. So we think that the mean is still 5.5. We have this t-value at the top. That is the test statistic. That's the sample mean minus the population mean divided by that standard deviation of the sample over the square root of the sample size. So that is that t-value. That is our test statistic. Then we have the sample mean, we have the sample standard deviation, and we have the number of things in our sample. But the quick way of doing this, as I said, if they ask you for a test statistic, this will run it, but you can always do that quickly on your calculator anyway using that formula. But remember that this time, because it's a t-test and we only know our sample standard deviation, that is what goes in the formula, not the population standard deviation. But if we want a quick way of knowing whether we're going to reject or fail to reject, we can just compare this p-value to the alpha value that's given in the problem.